were talking about dimension, and I was still talking about finite morphisms. And so the last thing, so the thing that I wanted to show you is the Noether normalization theorem. And so this says, so the first statement is if C of f in En is a hypersurface, so that means that f is a polynomial in x1 to xn, which is irreducible. So this would be a hypersurface. Then it follows that there is a finite surjective morphism let's say pi from z of f to an minus 1. Now, note that we will later want to see that finite surjective morphisms preserve dimension, and we want to see that the dimension of an is n minus n, so this would say hypersurface of dimension n minus 1. The second statement is that if x is any fine variety, then it follows there exists a finite surjective morphism n pi from x to some k, where k is some number which is at most n. Okay, for some. Okay, let's try to prove that. So let's start with this. So we have to find a finite morphism from here, which also is surjective. And so we first have to somehow normalize this f a little bit. So I call f d, so assume that d is the degree of f, and fd the top degree homogeneous component. So then it follows that fd is not the zero polynomial. Why is that? So this is a non-zero homogeneous polynomial. So, no, this is not what I wanted. fd of x1 to xn minus 1, comma 1 is not the zero polynomial. Why is that? So fd obviously is a non-zero polynomial because I take the top degree homogeneous component. And now if we put one of the variables equal to 1, there's no cancellations. We have as many monomials as before. The coefficients are the same. No? Have some ai 1 to n x1 to the I1 xn to the in. If you just put the last one equal to 1, all the terms are still there. No, we just have, it's no longer homogeneous, but otherwise it's the same. No? Is it obvious to everybody? No? If we have, anyway. So you can just see it contains as many components as before, no? Some A, I1, IN. But I'm not sure how to say it. Anyway, you can just check there are no cancellations. If it's not obvious to you, you should check it. Okay, so this is not 1. So we have seen before, if we have a non-zero polynomial, then we can find some point here such that the value at that point is non-zero. So thus there exists B1 or Bn minus 1 in Bn minus 1 such that f d of B1 Bn minus 1, is non-zero. This is a non-zero polynomial in x1 to xn minus 1. We can find something so that the value is non-zero. Now we can simplify our lives by kind of using a linear map from an to itself, so that this point B1 to Bn minus 1 actually becomes the point 0, 0, 0. So by the isomorphism from An to An, which sends the point A1 to An to A1 minus B1, An minus 1 minus Bn minus 1, An. So by this isomorphism, we can assume that B1 to Bn minus 1 is here. So if we compose with this isomorphism, will send this point here to the one where the first coordinates are 0. And we want eventually to find a morphism from the 0 set of f to n minus 1. So if we compose the map from the 0 set of f with an isomorphism of an with itself, it will not change our statement. Okay? So we have normalized it like this. So we have now, so that means fd of 0, 0, 0, 1 is non-zero. Now, obviously, the zero set of a polynomial and the polynomial multiplied by a non-zero constant is the same. So we can as well assume if this thing is non-zero, we can multiply the whole thing by the inverse of its value to obtain that it is 1. By the constant, we can assume that fd of 0, 0, 1, 1, what does that mean? If we take this this is the top degree homogeneous polynomial of f. So this has the property, if you put 0, 0, 0, 1 into this is 1. So this means the coefficient of x0 to the d is equal to 1. The xn to the d. Okay. And so this somehow now makes f to a monic polynomial in xn. So we can somehow see how we get to our final thing. So we take now pi to be just a projection given by x1 to xn minus 1 from the zero set of f to an minus 1. We just take the first n minus 1 coordinate. So now I write Wn to be the class, so this is an element in the coordinate ring C of f, to be the class of xf. So what do we have? We have, so then we have A of ZF will be equal to k x1 to xn divided by the ideal generated by f. And so this just means, I mean, we just have the, the simple algebraic extension, given by omega n, which satisfies this this equation given by f. So maybe I should have written it. So I first write this. So I just say this is equal to kx1 to xn minus 1. So this ring to which we have added Wn. No, this equation precisely, this monic equation, so let me write it out so that it's a bit clear. So we write f, I should have written that before, I can write this as xn to the d plus some I equals 0. So d minus 1, a I, xn to the I, where the ai are polynomials in k x1 n minus 1. And then you can see that if I take x1 to xn, kx1 to xn divided by this equation, this gives us precisely that this thing will be, at any rate, x1 to xn will not be changed, and here we have just added one more element, which is the class of xn. But I mean, at any rate, you can also say it, if you wish, you can say it differently, which is, you could also just say this would be the class of xi in this, if you wish. And then obviously this thing is originally generated by x1 to xn, and so after taking dividing by f, it's you generate by the classes of the xi. But I can write it like this. Anyway, so I have this equation. So we have this omega n is the class of xn, and this f looks like this. F lies in the ideal of x, so that means omega n satisfies this equation, where xn is replaced by.
But shouldn't we divide by
what?
Shouldn't we divide by Wn to the power d?
What? No, this is now just this. I add this element to it. It doesn't mean it's a polynomial in it. Like we did in algebra. You have an extension. You add. This is you have here a ring. We add an algebraic element. So this satisfies some equation, obviously. Namely, so this is maybe what you asked. Thus, in A of x, A of f, we have the equation. Zero, because f lies in the ideal, omega so w n to the d plus some I equals 0, d minus 1. Maybe I just write here p star of the I, w n the I, the p star is this projection. Okay, so in other words, Wn satisfies a monic equation over image here. So thus, so we see that A of ZF is obtained from the previous one by adding one element which satisfied the monic equation, and we had seen that this implies that this is a finite map. This was one of our limits. Thus, phi is a finite. Now, remember there was a part of the lemma or whatever it was which says that if we have an extension where we add one algebraic element which satisfies a monic equation, then the bigger ring is finite over the smaller one. This was a lemma before, and that's what we have. Okay, so this is a finite. So this is not quite enough because we want to find a surjective map. So we have to see the map is surjective. So again, we take some point, b1 to bn minus 1, so not the same as here, and a point in an minus 1. We have to see that there is some point lying over it. And we use basically the same trick as before, so that g of x be the polynomial where I put the first coordinates equal to this. And replace the last coordinate by x. So this is a polynomial in x. So we know that the coefficient of x to the d of this polynomial, of the original polynomial, was 1. And this is the leading coefficient in x. So that means this is not the zero polynomial. So as polynomial, the coefficient of x to the d of, or xn to the d of f is 1, we have the g of x is not the zero polynomial. So therefore, there exists a value for x so that we don't get 0. No, but that's not the point. Because I don't want to show it has points which are not light, because I want to actually find 0. So,
But if
so this is not 0, and it's a non-constant polynomial. That's what I want. It's not just a constant. If I have a non-constant polynomial, it has a 0, because now we want a 0. We don't want a 0. So thus, the 0 set of G is different from the empty set. So this is a subset of A1. So it has some zeros because it's a non-constant polynomial. However, then it means if I take p to the minus 1 of this point b1 to the n minus 1, this is equal to the set of all f of all p. So the first coordinates must be 1 to the n minus 1. And the last coordinate is some c, such that if I put it into f, I get 0. So this is therefore just e1 times en times e0 set of g, which is non-zero. So we see that the map is surjective because for every point in an minus 1, we find some points over it, namely precisely those which correspond to the zeros of this polynomial. Okay, so this was the first part. In some sense that looks like the easy part, but it's most of the work. Now the rest is some kind of induction. We want to show that every affine variety is a finite surjective morphism to some defined space. And then also that is smaller than n at n. So second statement is so we want to show that. So we want to show, just to remind you because I have it out. So x is in AN, and we want to show there's a map I from x to some AK, which is finite surjective. And we want to do this by some kind of induction over n using this fact that we have here for hypersurfaces. So assume, so we make induction over n. So if n is equal to 0, this is trivial. So x should obviously not be empty. So then x must be equal to a0, and the map is just the identity to a0. So thus we assume, and also obviously if x is equal to an, this is also trivial. Because again, just take that in. So thus we assume the empty set is different from x, and this is strictly contained in an for n is the principle. So then we can take, we want to reduce the hypersurfaces in some way. So we take a polynomial in the ideal of x. So let f in the ideal of x be irreducible. So first, as x is not equal to an, there are some elements in the ideal of x, and the ideal of x is a prime ideal. So if I would find a reducible polynomial in the ideal of x, then I could write it as a product of irreducible factors, and by irreducibility, by the fact that this is a prime ideal, it would follow that one of the irreducible factors has to be in the ideal of x. And so once I can find an element, I can find an irreducible element. So I can take any element in the ideal of x, any non-zero element, and take one of take one of its factors. So I have this. So we can look at the. So by 1, there exists a finite surjective morphism say pi from the zero set of f to n minus 1. And clearly, x is contained in the zero set of f because f is an element in the ideal of x. So we know that the inclusion x into C of f is a finite morphism, because we know that the inclusion of a closed subset is finite, so thus the composition tilde from x into Cf via the inclusion, and then this map pi, so this is pi, this is pi to an minus 1, is also finite. So we know, so this is a finite morphism, so we know that if you have a finite morphism, the image is closed. So that y in the n minus 1 is the image, which is a closed subvariety of the n minus 1. So then, by induction, there is a finite surjective morphism from y, which now lies in n minus 1, to some affine space of small dimension. By induction, is a finite surjective morphism I don't know how it's now called, maybe pi bar, from y to a k for some k 0 smaller equal to k smaller equal to n minus 1. And now we can just compose so if I take this map, p tilde from x, if I take it as a map to y, so it is still finite, so this is now, if I take it as a map to the image, it's still a finite map, as we know, we had this as an example, and now it's surjective because we have taken its image. So this is finite and surjective. And pi bar from y to a k is finite surjective. So the composition of finite maps is finite, and obviously the composition of surjective maps is surjective. So if I take this pi composed with this one pi bar from x, AK is finite and surjective. Okay. So as you see, I mean, it's maybe slightly confusing, but not so very much happens. We make this simple induction just to the properties, you know, how finite maps kind of are compatible with composition and things like that. And then it follows quite easily from the case of hypersurfaces. We don't need. And so that is the proof. We will soon use this, but now we first do a few other things. So this, the couple of next things is independent of the neutral normalization theorem. So we want to show, because this will be important later, that somehow, for instance, we want to show that finite morphisms have finite fibers. I've told you in the beginning that these are maps with finite fibers, so the inverse image of every point is finite, but I've given you a definition which a priori has nothing to do with it. And so now I want to see it. And so we do this in two steps. First, we want to show that it is kind of compatible with strict inclusions of closed subsets. So if something, if you have two closed subsets, one strictly included in the other, then also the images will be strictly included in the other. It cannot happen that the two closed subsets, one smaller than the other, get mapped to the same thing. And then we will see that this implies that the fibers have to be finite, because that somehow, otherwise there would be that leaves no room for bigger fibers. So this is the first statement, lemma. So let P from X to Y finite surjective morphism. So we still want finite surjective morphism. So let Z contain in W in X the closed subvarieties. So we take closed subvarieties of X, so irreducible closed subsets of X, which are strictly contained in each other, and then phi of Z is strictly contained in phi of W. So it cannot be that somehow two things become equal that were strictly contained in each other before. And normally if you have a map, this happens all the time. If you have if there's a fiber like this, and you have a point in the fiber, they are mapped to the same thing. Because they are in the fiber, you map to, and so this somehow will imply that all the fibers are finite, right? So, proof. So first, I claim we can assume that W is equal to X, and therefore phi of W is equal to Y. What is that? Now the embedding, so if I take the map W inside X to Y, this is a finite map. And it's also finite if I here then go to the image phi of W. If I instead let it go to the image phi of W. This map is also finite. And so if I just replace X by W and Y by phi of W, then we can assume that this is the case, and that W is X and phi of W is Y. And then we just have to see if you have a subset whose image is not the whole of Y, then if you have something, a subvariety which is not the whole of X, its image cannot be the whole of Y. So then to show, so let Z. Now we forget about the W. We just this is just X, but the Z we still call Z. So let Z in X be closed, and to show that phi of Z is strictly continuous in Y. No, where Y is still supposed to be surjective. The original map was still supposed to be broken. So we want to show this. So if Z is not the whole of X, then phi of Z is not the whole of Y. And obviously we somehow have to use the finiteness. Because if the map is not finite, this is obviously not true. So z is not equal to x, so we can choose a function in a of x which vanishes on z. No? Because this just means that G lies in the is the class of an element in the idea of z, no? Which is bigger than the idea of x. So this G is an element of A of x. So, you know, as A of x is a finite, whatever, phi upper star of AY algebra, it satisfies a monic equation. So then G satisfies an equation G to the n, I bring it to the other side, is equal to sum I equals 0 to n minus 1 phi of phi upper star of AI G to the I, where the AI are some elements of 1. This is the statement that this is a finite map. So every element in AX satisfies a monic equation. So if it satisfies such an equation, we can choose such an equation such that this number n is minimum. Not minimum. Okay, we've chosen this. Now, then it's clear that phi star of A0 cannot be 0. Because if phi star of A0 is 0, then we just divide by G and the equation is still satisfied. Then G to the n minus 1 will satisfy such an equation. So then phi star of A0 is different from 0. Otherwise divide. Which contradicts the minimality of this power.
Do we assume that G is not 0 in AX?
Yeah, well, I think so. Let me see. Well, okay. Yeah, maybe I can assume that. I mean, I have to assume that. You know, I certainly want to assume that because I want to say that we have some strict inclusion. So we want really. So this is supposed to be a strict inclusion. So we want to we therefore find a non-zero element which does it. So this is how without 0, this is how one uses the assumption. If I put the 0 here, I haven't. There's nothing. I mean, I certainly cannot conclude anything from that, but thank you. So now, however, if we do this, we can now bring this to the other side. So it follows that phi star of A0 is equal to minus G. So let me see. We bring this over. Maybe it's the other around. I think I have the signs are not quite right. Anyway, so I do this. I bring everything to the other side. I only leave the G0 here. So that means this is equal to G. I mean, first this would be so G times G to the n minus 1 minus sum I equals 0 to n 1 n minus 1 phi star of AI times G to the I minus 1. No? I bring this with E0 to the other side, and I pull out the G, because now everything has a common factor G. So we see that this means that this thing lies in the ideal generated by G. So that means if I take, so G was lying, G restricted to Z is equal to 0. So this lies in the ideal generated by G. So this thing vanishes on Z. So if I take phi star, so it follows that phi star of 0 restricted to Z is 0. Which is equivalent to saying that if I take E0 restricted to phi star to phi of Z, this is also equal to 0. And so we have found our element A0, which was not 0, and in fact even its pullback was not 0. So A0 is not 0 in AY, because even its pullback is non-zero, but restricted to phi of Z is equal to 0. So A0 is different from 0, thus it follows that phi of Z is strictly contained in 1. Okay, so it's a bit tricky, but anyway, so this is the argument.
Just a question. How do we guarantee that there exists G which is not 0, like that this happen?
Which one? Where?
The first one.
Here.
Yeah. Why can we assume that G is not 0?
Well, we have that so Z is strictly contained in X. We have assumed that. So that means it follows that, for instance, if I take the ideal of X, this is strictly contained in the ideal of Z. No, because we know that Z is the zero set of the ideal of Z, and X is there, so they have to strictly include. So I just take G. So I take G tilde in the ideal of Z, modulo the ideal of X, and then G is the class in AX of that. And this will be a non-zero element, so G, this was clearly different from 0, and it vanishes on Z. Okay, so this is something which, in some sense, I almost would like not to have to say. But on the other hand, it's maybe good to say it at least a few times. Okay, so this was this result. And then now we, as a corollary, we get this thing that I said. Phi of X to Y is finite morphism. And then all fibers e to the minus 1 of y with y in y are finite. Okay. And we will use this thing, I'm just writing out. So. First we can assume P is surjective, because So obviously, if I take a point in Y which does not lie in the image, the fiber is empty. In particular, it's finite. If I can therefore just replace Y by the image, and then the map is finite and surjective. And then you have to show there that all the fibers are finite. So we can assume this. Okay. So it's enough to show that every irreducible component Z of phi to the minus 1 of Y is a point. So, I mean, the phi to the minus 1 of Y for a point in Y, for Y in Y. So the fiber phi to the minus 1 of Y is obviously, it's the inverse image of the point, so it's a closed subset of X. So it's a variety, it's an algebraic set, and so it has finitely many irreducible components. If every of these irreducible components is a point, then it consists of finitely many points. So I take just a point in this thing. Then we just have then phi of Z of the small point Z is equal to phi of Z, obviously, because it's Z lies, namely Y. So by the lemma, if we have two closed subsets strictly contained in each other, then the images cannot be equal. So the only way how this can happen, as Z is contained in Z, if small z is contained in large Z, is that small z is equal to Z. That follows Z is equal to. No? Okay. So this was if there are no questions, this was as much as I want to say about finite morphisms, and now I want to apply them to dimension. So I have to determine to you, define for you what dimension is. There are several different definitions available which are equivalent. I choose the most geometric one, which is maybe sometimes called whole dimension, which is in terms of closed subvarieties, how many closed subvarieties you can stack into it, one smaller than the other. And then we want to show that this dimension satisfies the properties we expect. And dimension. So let X be right. So maybe I just start with the definition. So, I mean, anyway, the idea is that if you have a variety and you have a subvariety of this variety, that the dimension of the subvariety should always be smaller, strictly smaller. And the actual dimension, and you do it minimal with this property. So the dimension of a variety will be kind of the length of a chain of subvarieties stacked in each other, so that you cannot squeeze anything in between. So let me write this down. So let X be variety. So this could be affine or projective, or quasi-affine or quasi-projective, and we look at the chain of closed subvarieties. So first one is not empty, contained, typically containing x1, and so on, x2. Xn equals x, be a chain of irreducible closed subsets. So we were to, it's not a big difference, but we just say then that x0 until xn is a chain in N. Right. Saves us a few seconds. So later we will see that such chains always have to be finite for varieties, but in the moment we cannot know that, so we have to, we'll see relatively soon that such chains always have to be finite. But what we need is that there is a kind of, that they cannot be longer than a certain number. And this is not clear at the moment, we'll prove it later. So therefore I make a slightly more complicated definition, but in the end it will be simpler. So if there exists a maximal n such that such a chain exists, we say the dimension of x is the dimension of x equal to this number n, so the length of the maximal chain. Otherwise, so that means if there exists no maximal such chain, we say the dimension of x is infinity. We will later say that this second case never happens for the varieties like we defined them, but for the moment we haven't proven this, so we have to kind of, in order to not have a circular reasoning, have to kind of keep this as a possibility. So you first want to show, so this is the definition. So the idea is just whenever you have a subvariety of a variety, it really is smaller, and it's smaller in the sense that the dimension is really at least one less. So remember. So first we want to see that finite surjective morphisms preserve dimension. After what would have been the whole point of studying them in order to do dimension if they have nothing to do with it. So, so we first have the following statement. So if y in x is a closed subvariety, of a variety x, then dimension, this is kind of trivial from the definition, of x is first or smaller or equal to the dimension of x, and this is strict if this dimension is not infinite. as I said, this case actually does not happen. So in fact, it will be always strict, but for the moment we have to carry it along. And this is used for what I announced, namely that f from x to y, the finite surjective morphism, then what? Oh no, we are not yet there. This we get later. So a closed surjective morphism. So this is not, the result will come later. Then the dimension of x is bigger or equal to the dimension of y. You know, you would think so, no? If you have a surjective map, the dimension of the image should be smaller than the dimension of the source, or smaller or equal. We will later see if the map is also finite, then we have equality. That comes later. So first let's proof here of this is relatively easy. So the first one is quite simple. So if y0 and so on to yk is a chain in y, then I can add x to the chain to make a longer chain. Which is long. So for every chain in y, I can find a longer chain in x. So this will show that if there is a maximal chain in y, then this has it's bigger. So that dimensions that include that the dimension of x is bigger than that of y. But if it's infinite, then we cannot conclude infinite. You know, the way we look at it here, it could be that both are infinite, and so they are in that sense equal. Okay, now to 2. So here, we want to say that if we have a chain in y, we can find a chain in x which is possibly longer. So therefore we want to use a chain in y to construct a chain in x which has at least the same length. And so the maximal chain then would, if anything, be longer. So let y0 yn be a chain in y. I want to show there exists a chain x0 xn in x, or the same length, such that each xi maps surjectively to the yi. So with f of xi is equal to yi for all I. So that will then imply that the dimension of x is bigger equal to that of y, because given any chain, we have found a chain in x which is at least as long. So, and we want to do this induction on n. So apply induction on n. So we make a okay. So we want to, for instance, we do want to do for y0 to y1, for each of them we want to find inductively such a chain. So if n is equal to 0, there's nothing to. So yeah. I mean, we could just maybe in this case it's not so. Normally here, well, anyway. So let's do the induction step. So we start with n minus 1. Let z1, so zn, zr. So the point is we cannot just take the pre-image of the yi because that would not be necessarily reducible, but we can just take a suitable irreducible component. So let's leave the irreducible components. Of f to the minus 1 of y n minus 1. Then obviously y n minus 1 is equal to f of z1 union f of zr. Because f to the minus 1 of this is the union of these. So y to the n minus 1 is irreducible, and these are irreducible closed subsets. So, I mean, anyway, these are closed subsets. I write an irreducible set as a union of closed subsets, so it must be equal to one of them. So, as y to the n minus 1 is irreducible, there exists an I with f of zi is equal to y n minus 1. Okay, so this maps. Now we can apply the induction hypothesis with the yn minus 1 and this. So there must be, so apply to find that there exists a chain of irreducible closed subsets such that each closed subset here maps to the corresponding yi. So to get a chain, x0 contains in x1 until xn minus 1, which is the ci, with f of xi is equal to y for I. And now obviously we can again put x at there. will satisfy our assumptions. We get a chain, so that is a chain as we have to specify. Okay, so because and so this shows that indeed the dimension of x is bigger or equal to that of y. Because for every chain in y we can find one which is at least as long in x.
How can I show f of z I is closer?
Oh, I mean, this is, we already know that, I mean, we have assumed that it's a closed morphism. Yeah, I need this assumption. But I maybe didn't stress it enough, maybe also didn't write it critically enough, but this is a closed surjective morphism. So, obviously, if I don't have that this morphism is closed, then I couldn't conclude anything. That's why we will want to, while we proved that finite morphisms are closed, because then we can apply it to finite morphisms. Okay, and so it's not so surprising that now we want to apply this to show that finite surjective morphisms preserve dimension. This is also that f x to y is finite surjective morphism. Then the dimension of x is equal to the dimension of y. To prove, we've just shown that if we have a finite and closed morphism, then the dimension of x is bigger or equal to that of y. So the dimension of x is bigger or equal to the dimension of y, because f is finite and closed. So we have to show the other inequality. So we show the dimension of x is also smaller or equal to that of y. So let's take a chain in x. Chain in x, and we put yi to be the image. Then we know that as this is strict inclusion, and this is a finite surjective morphism, or a finite morphism, we also get, no, finite surjective, we also get strict inclusions between the yi. So the yi are closed and irreducible. That we know because the image of something irreducible is always irreducible, and they are closed because of closed map. And yi is strictly contained in yi plus 1, or I, because f preserves strict inclusions of irreducible closed subsets. irreducible closed subsets. So then, so therefore we get a chain. So thus y0 contained in y1 and so on is a chain in 1. Okay, so this is reasonably straightforward, and so this shows that the dimension of y is bigger than that of x. Okay. So with this preparation, we will now be able to prove the most obvious fact that an has dimension n. And this then will also imply that this assumption we made at the beginning, that, or the statement that, that the dimension could be infinite, that this cannot be, because at least to begin with, every affine variety is a subvariety of some affine space. So if we show that an has dimension n, then every affine variety which lies in an has dimension at most n. Okay. So we would again, and this obviously uses the Noether normalization theorem, but anyway, so we have the following theorem. See, we have first dimension of an is equal to n. The second is that if I have a hypersurface, or that f in k x1 to xn, the polynomial of Dvn, irreducible polynomial, well, of some degree, of positive degree. So it should not be a constant polynomial. And then the dimension of the zero set of f is precisely n minus 1. So one less. And also conversely, if I have a subvariety of an which has dimension n minus 1, it's the zero set of one polynomial. Any subvariety x in n of dimension n minus 1 is a hypersurface, so a zero set of an irreducible polynomial. Okay, so this is a little bit tricky, so let's see. So first, we want to see that if we know 1, we know 2. That's easy. But we will need it later. So let's take that. So that f, that's basically by definition that f in, or by the Noether normalization, take f such an irreducible polynomial. So by Noether normalization, a theorem that exists with finite surjective map morphism P from the 0 set of F to an minus 1. So thus, the dimension of the 0 set of F will be equal to the dimension of an minus 1. Okay? And so if we happen to know that this dimension of an is n, this would mean that dimension is n minus 1, but we actually need it in this form. So let me see. Well, I can try to do it. It's a little bit, nothing really happens, but it happens in a somewhat complicated way. And we will want to use this step here to make some kind of induction. So so we have to show the dimension is precisely equal to n. So one inequality is easy. You can find a chain. The other is that the length of the maximal chain, it can be at most n. That's the difficult part. So let z of I, di, be the 0 set of xi plus 1 until xn in n. I just let the last few coordinates put them 0. Then we see that the 0 is strictly contained in 1. So we find, and these obviously, Zi is isomorphic to a to the I. These coordinates, the last n minus I coordinates are 0, so this thing will be isomorphic to a to the I, just via the obvious method. So Zi thus is reducible. So this is the chain of length n in A. So thus it follows that the dimension of an is bigger or equal to n. Now I have to show the other direction. So show dimension of an is smaller or equal to n by induction on n. How does that go? So the case n equal to 0 is trivial, because A0 is a point, and obviously there's nothing you can put there, so the length of the maximal chain is 0. So the induction can start, and so by induction assume that the dimension of an minus 1 is equal to n minus 1. And now let's take a chain in xn. x0 strictly contained x1, some xk. I call it xk minus 1 for some reason. In an, the chain for an. So it doesn't have to be maximal, it's just some chain. And we want to show that this k can at most be n. And so this thing I also call x. So then x contained in AN is an irreducible closed subset. So we again can take an equation for it. So we take an f which lies in the ideal of x, which gives us a hypersurface. So we want to somehow use hypersurfaces. And again, as the ideal of x is a prime ideal, we can take an irreducible polynomial in this ideal of x. So that f in the ideal of x is irreducible. Okay, which also implies it's not zero. So we take this. And we use the same argument before that we can take it to be irreducible. And now we just have to, well, I expect you will remember statement. So as now we see x is contained in the zero set of f, because f lies in the ideal of x. We know
Can't we say that because there is a surjective finite morphism from Z of f to some affine space, then the dimension of Z of f is the same as dimension of some affine space AM, but because of this we have that M must be less than N. Therefore, by induction we get the first part is at most N minus 1.
That could be. I mean, I didn't quite follow, but I mean, yeah, I think it would work like this. I write something, I do it slightly differently, but I find it. So I wanted to do it a different way because it's actually quite simple also directly. We don't really need to use the, I mean, we use what we have deduced from the neutral normalization theorem, but we don't need to use the neutral normalization theorem again. So we have this contained in it. So we have, so therefore the dimension of ZF is bigger or equal to that of X, and the dimension of X is at least k minus 1. So we find that k minus 1 is smaller or equal to the dimension of ZF, which by this part that we had called 1 to 2 was equal to the dimension of the n minus 1, which we know by induction to be n minus 1. So thus k is smaller or equal to n. And so that means any chain in AN can have, at most have length n. So the maximal length of a chain is n. So the dimension of AN is n. So here actually is smaller or equal to n, but we have already shown it's bigger. Okay, so I don't know how this. So the last bit is kind of trivial, that every subvariety of dimension n minus 1 must be hypersurface, namely you just use the same trick that we used before. If you take the zero set, so that's the same, so as x in the n closed, there is an irreducible, so strictly complete and irreducible polynomial f in the ideal of x, with x is contained in the zero set of f. But as the dimension of x is equal to the dimension of the zero set of f, and both are irreducible, we have seen if you have two irreducible things, one contained in the other, which have then, if they are different, the dimension must be different. I mean, now they are equal to the dimension, so the dimension is equal, so they must be equal. It follows that x is equal to 0. Okay. So this is maybe enough. So next time we will make more case. We will see how one computes the intersection of first a closed variety with a hypersurface, and then we also have to go to the projective case. But anyway, it's enough for now. I'm sorry I didn't give you back your